In the last half of 1964, Centaur reached the midpoint in its flight test program, only 2 flights away from operational status. Program activity centered on resolving problems of the AC-3 flight, ground testing in support of AC-4, development of new hardware and systems for the approaching operational missions, preparation of new launch and test facilities, and the flight of the 4th experimental Atlas Centaur AC-4. During the period, much of the ground testing was directed toward removing launch constraints assigned to AC-4. 2 of these constraints were assigned as a result of the previous AC-3 flight test.
AC-3 successfully demonstrated its flight worthiness and unique system for jettisoning its insulation panels and nose fairing. However, 2 malfunctions did occur which became the focal point of investigation after the flight. The first occurred during jettisoning of the nose fairing. The nose fairing protects the spacecraft from aerodynamic loads and friction heating during ascent through the atmosphere. The jettison system performed satisfactorily as programmed. However, at jettison, telemetry data showed an adverse environment in the payload and forward bulkhead areas. Shortly thereafter, data recorders registered a momentary shock to the guidance system. Analysis indicated that when the nose-fairing thruster bottles fired, they generated a pressure pulse which caused the recorded shock.
To fix the problem, engineers first reduced the pulse intensity by decreasing the thruster bottle pressure and by making the nozzle area smaller. With decreased pressure, jettison thrust is less and continues for a longer time to assure separation. Strengthening and overlapping the deflector bulkheads ruggedized the fairing structure. Then at the Lewis Research Center, the modified nose fairing and jettison system underwent extensive testing in the space chamber. Under a vacuum which simulated the space environment, the fairing jettisoned as programmed. Meanwhile, at astronautics, other tests were conducted to see if the shock wave transmitted through the fairing hinges would cause a disturbance to the forward bulkhead and payload. The test setup consisted of a Centaur tank with a surveyor mass model and dummy electronic packages mounted on the forward bulkhead. Shakers attached to the nose fairing hinges vibrated the tank. Results indicated that the fixes made to the fairing would significantly reduce the shock so it would not adversely affect the bulkhead area. Confidence in the fixes removed one of the constraints to the AC-4 flight.
The Atlas booster portion of the AC-3 flight ended when the sustainer engine cut off as programmed. Centaur separated and its main engines ignited. At this point in the flight, telemetry data showed a malfunction in the hydraulic power package. The vehicle began to roll and subsequently the engine shut down. The hydraulic package provides power for controlling movement of the C2 engine. This was apparently an isolated failure in a unit which had performed well in over 60 ground tests in simulated operating environments. Post-flight testing revealed that an engine seal could have leaked hydrogen, thereby creating an extremely cold environment in the area of the hydraulic pump shaft. Test labs, however, could not duplicate the failure, regardless of temperature conditioning.
It appears that the malfunction resulted from a combination of cold environment and an out-of-tolerance drive chain or coupling. Engineers subjected materials used in the coupling to cryogenic temperatures under operational stress loads. Results indicate that a metal coupling with a metallic bellows and diffuser would provide greater reliability than the nylon coupling formerly used. In this area, the spinner portion of the coupling throws off any leakage, keeping cryogenics away from the pump shaft. The modified unit, tested in an environmental chamber, operated well under conditions in excess of those it will experience in flight. During engine tests at Pratt & Whitney and at Sycamore Canyon, San Diego, The hydraulic power package performed satisfactorily. The final run, a 335-second composite test, removed another launch constraint.
Other flight constraints assigned to AC-4 resulted from the requirements of its more complex in-flight sequence and mission objectives. AC-4's primary test requirement is to inject the Centaur upper stage into a circular orbit on a one-burn, direct ascent trajectory. On previous flights, Centaur flew a trajectory planned to insert the vehicle into orbit at about 300 nautical miles. For AC-4, orbital insertion is planned at about 90 nautical miles. As a result, Atlas Centaur remains in the Earth's atmosphere longer and experiences increased aerodynamic loads and heating as it pushes its way through the denser regions. A series of tests at NASA Lewis and Astronautics reaffirmed the structural integrity of the vehicles, demonstrating their ability to withstand the increased aerodynamic effects. The most important primary objectives of the AC-4 flight test are to verify the performance and structural soundness of the nose fairing and insulation panel systems, demonstrate overall vehicle structural integrity, and demonstrate the guidance system accuracy, performance, and system integrity. For AC-4, the all-inertial guidance system will operate in a closed-loop capacity for the first time. It will assume command at booster staging and will direct Atlas Centaur, controlling flight events aboard both vehicles. Before Centaur's guidance system could be considered flight-ready, it had to pass a series of design proof tests at Astronautics.
Since June, we subjected the guidance set to 12 different proof tests. 9 of them have been an exposure to a severe environment. The first 6 had to be completed before AC-4 could fly. These included performance, temperature, shock, acceleration, and vibration checks. The 6 design proof tests constraining the flight were completed in September.
AC-4 is also the first Centaur to fly a mass model of the Surveyor spacecraft. The 2,100-pound model is a relatively simple structure and represents the Surveyor only in weight and center of gravity location. It will not separate from Centaur during flight. With most of the ground tests complete and only a few constraints remaining, the Surveyor model, Atlas 146D, and Centaur 4C were airlifted to the Eastern Test Range.
After systems checkout, launch crews mated the vehicles on 20 August. Tests were progressing with launch scheduled for October. In early September, Hurricane Dora threatened the Cape, and as a precautionary measure, test range crews removed the vehicles to a safe area. AC-4 was down for 8 days. In October, launch was again delayed when, during an integrated tanking test, the AC-4 liquid oxygen tank overpressurized. A faulty liquid level sensing tube gave a false reading and continued pouring liquid oxygen into the already full tank, developing overpressurization. X-ray leak checks did not reveal any defects or ruptures in the tank or bulkhead. With confidence in the tank's integrity, crews recycled checkout procedures and began guidance launch alignment, the last constraint to the AC-4 flight. AC-4 is the first Centaur to employ optical alignment to orient the guidance platform into the selected launch azimuth. A light beam leaves the optical equipment shelter and enters the nose fairing through an optical window. It then strikes a reflective prism on the inner gimbal of the guidance platform. An operator remotely positions the inner gimbal until the prism reflects the beam back to an alignment theodolite. The platform then locks into a stable position to provide inertial reference during flight. Optical alignment is about 5 times more accurate than gyro compassing used on previous flights. The theodolite holds the guidance platform captive until 15 seconds before launch. December 11, 9:25 a.m.
All recorders are fired. 14 seconds. Initiating engine start. Minus 8. Please start. Ignition. Release. Looks good. Right in the broken. We have a little water on the pad. Looks good. Deco. Jettison booster.
I'm Andrew Kaltinsky, Assistant Program Director of Centaur for Engineering here at General Dynamics Astronautics. This flight was the most heavily instrumented to date. Of the 650 telemetered measurements aboard Atlas and Centaur, 99% yielded usable data. This was the 26th consecutive successful flight of an Atlas booster. The operation of all Atlas systems were nominal throughout booster phase. This was the first Atlas Centaur flight with Centaur all-inertial guidance in flight command. At booster cutoff, the guidance system controlled both Atlas and Centaur for the remainder of the flight. The insulation panels and nose fairing jettisoned smoothly at the prescribed times. Atlas and Centaur separation and Centaur main engine ignition was equally smooth. At T plus 573 seconds, Centaur main engines cut off as predicted, and the vehicle then began a controlled coast in a near-perfect circular Earth orbit. At this moment in time, we had achieved all the primary flight test objectives. We also had again demonstrated a single burn, direct ascent type mission that will satisfy the presently planned operational flights scheduled to place Surveyor on the Moon. However, concurrent with our Surveyor flight test program, we're looking towards the future when it will be desirable to have a two-burn capability. That is, Centaur will coast in a parking orbit for a time following the first burn. The engines will ignite again and thrust the payload into a lunar or planetary intercept trajectory. The two-burn approach will give us a considerably broader launch window. However, the coast phase imposes a number of technological unknowns. In order to acquire advanced experimental data on the behavior of cryogenic propellants in the zero-G coast period, we added a coast experiment and a planned engine restart as secondary flight objectives for AC-4. At the beginning of the coast period, the propellants float free in the vehicle tanks. Two small ullage rockets mounted on the aft end of the vehicle, capable of 4 pounds thrust, were commanded to start at main engine cutoff. The engines were designed to apply forward thrust to settle the propellant in the aft end of the tanks, ready for the second burn. The AC-4 flight results indicate that the 4 pounds thrust is not sufficient. The thrust level selected was based on the interpretation of tests with small-scale tanks in a short-duration zero-G environment. These small-scale tests did not give us accurate data reflecting propellant behavior in a full-scale tank in a true space environment. The AC-4 vehicle maintained attitude during the coast period until the hydrogen tank vented 267 seconds after main engine cutoff. There is evidence that the propellant had not settled completely. Liquid hydrogen exited through the vent valve and in the vacuum of space expanded with a force much greater than if the gas alone had been venting. Gas impingement on the forward end of the tank then pushed the vehicle in yaw
with a force greater than the attitude control rockets could handle. As a result, the vehicle began to tumble, further aggravating the problem of keeping the liquid hydrogen at its pump inlet. All pre-start commands were initiated, indicating that all systems were functioning normally, but engine start was not achieved due to propellant starvation. As a result of the AC-4 experiment, we acquired vital information relative to propellant behavior. This is not only valuable to future Centaur two-burn designs, but to all space programs that are using cryogenic liquids in a zero-G space environment. Thus, in addition to achieving our primary mission objective, the flight advanced to state-of-the-art in the use of cryogenic propellants in space technology.
The upcoming flights of AC-5 and 6 will be dress rehearsals for the operational performance of AC-7, scheduled to place the first surveyor on the moon. AC-5 and 6 will verify flight results to date and demonstrate the performance of new systems and hardware. They are scheduled to fly with an advanced propellant utilization system and a new Agena-type flight programmer. The Atlas launch vehicle will fly with upgraded booster engines for the first time on a Centaur mission.
Atlas-operated MA-5 engines will now produce 390,000 pounds of thrust, an increase of 30,000 pounds over the earlier launch vehicle. Specific impulse is rated at 251 seconds. The uprated propulsion system has proven itself in more than 31,000 seconds of ground and airborne operation. In the next test flights and for all operational missions, Centaur is scheduled to fly an advanced propellant utilization system. The system consists of electronic sensors and a computer which controls propellant flow to produce a balanced mixture to the C2 engines. Proof tests measured the redesigned probe's ability to accurately determine propellant levels in the tanks. Without simultaneous depletion of fuel and oxidizer, residual propellants in the tanks could amount to several hundred pounds of useless baggage, energy available but not used. At the end of December, the last of the design-proof tests were underway. At the request of the National Aeronautics and Space Administration, Astronautics has adapted an electromechanical programmer for Centaur. The unit replaces the electronic programmer presently used. It consists of two main components, an Agena mechanical timer supplied by Lockheed, and an interface system which contains electronic modules, relay logic, and a power supply developed by GDA. The mechanical timer, selected because of its long history of highly reliable performance, replaces a solid-state digital clock. The Agena timer contains a synchronous motor which operates switches to signal in-flight events. The electronic programmer, however, will still be retained as a backup. It can stand in for the Agena unit without additional modification to Centaur.
The main objectives of the AC-5 and 6 flights will be to place a dynamic model of Surveyor into a simulated lunar transfer trajectory. The Surveyor model will separate from Centaur and fly on a course in the direction of an assumed or paper moon.
The dynamic model consists of three main assemblies: space frame, a retromotor simulator, and an S-band transponder. The Surveyor model is non-functional, except for telemetry and tracking equipment and instruments that measure in-flight environment during the boost phase of launch. Shortly after the Surveyor model separates, Centaur will perform an in-flight turnaround and retro maneuver. Residual propellants will discharge unignited through the main engines, slowing Centaur down to increase the distance between it and the payload. On operational flights, this maneuver will prevent Surveyor's guidance from locking onto the tank as a navigational reference.
Another important objective of the upcoming flights is to demonstrate launch-on-time capability. Atlas Centaur must be able to launch at predetermined times and days when the Earth and Moon are in proper relationship to each other. To help meet the launch on time requirement, Astronautics is activating a combined systems checkout facility. Until it is completed, a modified checkout dock in the factory is being used. Atlas 156D and Centaur 5C completed factory acceptance and moved into the new interim combined systems test stand for composite systems checkout. In this facility, an Atlas Centaur composite test duplicated actual pre-launch and flight conditions as near as possible to demonstrate overall systems compatibility.
The interim stand demonstration reduces on-the-pad time required for pre-flight checks at the Eastern Test Range. It also provides a higher level of confidence in the combined systems than is possible through individual checkout tests. After AC-5 finishes composite testing, it will leave for Cape Kennedy in January 1965. Ultimate in the Centaur ground test program will be a combined systems test stand built for NASA adjacent to astronautics. The combined systems stand, now 98% complete, will house an Atlas in a horizontal fixture. Centaur, with surveyor mounted on top, will stand vertically on an interstage adapter. All three will mate electrically and function as if on an actual mission. Composite test crews will use the factory interim stand until the new facility becomes operational early in '65. AC-7 is scheduled to be the first Centaur to occupy the new test stand.
The AC-6 R&D configuration represents the operational design for one-burn missions. A number of major changes were incorporated in the AC-6 flight vehicle tank and structures.
They reduced tank skins from 16 thousandths to 14 thousandths gauge steel, cutting tank weight 38 pounds. The intermediate bulkhead moved aft 4 inches, shortening the liquid oxygen tank and increasing the liquid hydrogen tank capacity 26 cubic feet. Repositioning the bulkhead aft eliminated the oxygen tank slosh baffle and the heavy attach ring. The attitude control clusters moved from the attaching ring to the aft bulkhead, eliminating the need for cutouts in the interstage adapter. Modifications to the aft end of the tank required the development of a new linear-shaped charge system. The charge cuts the adapter for separation at Atlas Centaur staging. Heater blankets and cryogenic liquids in the tank simulated aerodynamic flight conditions. The charge severs the adapter flange and gravity separates the two. The third and final test in the series satisfied all test requirements and proved the system flight-worthy.
At the end of 1964, manufacturing had begun on nearly all Centaur vehicles at Astronautics. And at the Eastern Test Range, Complex 36B was nearly complete.
In December, AC-6 was about 90% complete in final assembly. AC-7, the first operational Centaur scheduled to place a surveyor spacecraft on the Moon, is about 60% complete in final assembly. Centaur tanks for AC-8 through AC-13 are in various stages of fabrication. AC-8 received its propellant utilization sensors before moving to the final assembly docks. For AC-9, assembly crews completed all welding on the Centaur vehicle tank, sealed it, ran pressure leak checks, and prepared it for shipment to the main plant for final assembly. AC-10 is in the major weld fixture. The forward bulkhead and first skin section are in place. The tank is near ready for the intermediate bulkhead. AC-11 consists of a forward bulkhead and first skin section. Forward bulkhead buildup is underway for both AC-12 and 13. At the Eastern Test Range, the ground support equipment task at Complex 36B is 98% complete. Many of the electrical launch control systems have been validated and sold to inspection. Only a few large mechanical components remain to be installed.
In the past 3 successful flights, Centaur has demonstrated its basic flight worthiness and its ability to fly a one-burn direct descent mission. The single-burn mission satisfies the launch requirements for all present Surveyor operational flights. Today, the bulk of Centaur's research and development is completed. Its operational payload capability will be 25% greater than initially planned. The major remaining development involves achievement of a 2-burn mission capability. Attention will be focused on coast phase and engine restart experiments. In 1965, with the successful flight of AC-6, Centaur will be operationally ready.